So we started functional dependency. So we have the definition, so we know what a functional dependency means. So that we have seen. So say given a functional dependency set F say specified on relation R. Now from these, some other functional dependencies can be inferred. But for this inference, we have certain inference rules. Inference rule 1, we can refer them either by the number IR1 or by the name. The flexibility rule, it says that X implies Y if Y is a subset of X. Obviously, these X, Y all are part of the schema R. So this is reflexivity rule. If Y is a subset of X, then always X implies Y, it holds. IR2, that is the augmentation rule. It says that if X implies Y, then Wx implies Wy. Both sides, it has been augmented by W. IR3, transitive rule. Says that if X implies Y and Y implies Z, then X implies Z. These three are known as Armstrong's axioms. IR4, decomposition rule. If X implies YZ, then X implies Y, similarly X implies Z. It is decomposed. IR5, union rule. If X implies Y and X implies Z, then X implies YZ. IR6, pseudo-transitive rule. If X implies Y and WY implies Z, then WX implies Z. Now, to infer additional functional dependency from the set F, one can apply IR1 to IR6. These inference rules we can apply to infer other functional dependencies. Now we can go for proving these rules also. Say, if we think about the first one is a trivial one. This is also known as trivial functional dependency. Say, if we try to prove, although the axioms are normally not proved, still if we go for doing that, see, this is pretty simple. What we are supposed to show that if we have tuples belonging to the state of the schema on which the functional dependencies are defined. Suppose we are talking about the schema R, then X implies Y. We say that is, if T1 X equals to T2 X, then T1 Y must be same as T2 Y. Now, as T1 X equals to T2 X, and Y is nothing but a subset of X, then obviously T1 Y equals to T2 Y. So this is very trivial because Y is part of X. So X same means the subpart of X, that will also be same. So this is simple. Let us go for IR2. Say X implies Y holds. So we can have tuples, say, on which T1 X equals to T2 X and T1 Y equals to T2 Y. This is because as X implies Y holds. Now, say T1 WX equals to T2 WX. Now we have to show that T1 WY is equals to T2 WY. We go by contradiction. Let WX doesn't hold. Then what does it mean? Say, as if T1X equals to, T1WX equals to T2WX, but T1WY not equals to T2WY. So we are going by the contradiction. Select these things. Then if these are same, even then they are not same. Let us see whether this is possible or not. Now from here, say T1X equals to T2X, T1WX equals to T2WX. So if I say this is A, this is B, A and B, consulting A and B, you can say WX, T1 WX, T2 WX is same, part of X, they are same, then obviously T1 W equals to T2 W. Now if this is C, say this is D, then C and D, it gives us T1 Y equals to T2 Y. Sorry. Consulting these things, we can find that T1 WY equals to T2 WY. So it is not possible. if we have two triples for which these things are same and x implies y holds, then these will also be valid. Right? So that is the proof for IR2. That is the augmentation rule. Now if we go for IR3, that x implies y, y implies z, this holds. So we have the tables T1 y equals to, from this one, if we have two tables T1 and T2 such that this thing holds, this is true, then this means T1 y equals to T2 y. But from here, if we find that as y implies z holds, so if T1 y equals to T2 y, then T1 z equals to T2 z. So now we are finding a table T1, T2, where the value of x is same, then value of z is same. Right? So now taking these two, you can say x implies z. Now, these are the extension, so that if you go for inference, it is not necessary all the time we will be starting with the axioms. So we can go for applying these things also. So this can be proved taking help of the axioms. Say if we think of IR4, x implies yz, this one holds. We'll have to prove x implies y. Now see, this is pretty simple. Yz implies y. This is by IR1. This is a subset of this. This is a subset of this. So by IR1, by reflexivity rule or trivial rule, we can say yz implies y. So x implies yz, yz implies y. Now on these two, if we apply the transitive rule, x implies this thing implies this. So x implies y. Right? So that is IR4. If we go for IR5, union x implies y, x implies z. See, if we apply augmentation rule, so xy implies yz. So on this one we have applied IR2, both sides augmented by y. So xy implies yz. Here, if we again we are applying IR2, this is augmented by x. So x augmented by x is same. So here x implies xy. Now if we consider these two, apply the transitive rule. So we have obtained x implies xy, xy implies yz. So basically x implies yz. Applying IR3 here. Okay. If we think about IR6, pseudo-transitive rule, x implies y and wy implies z. We have to prove wx implies z. So first of all, let us apply IR1 augmented by w, so it becomes wx implies wy. So now we have wx implies wy, wy implies z. So on these, applying the transitive rule IR3, So it becomes WX implies Z. So given a functional dependency set on a relation, we can infer other functional dependencies applying these inference rules. Say set of FDs F specified on R. F plus is closure of F. It is nothing but set of all functional dependencies that includes F and FDs that can be inferred from F. So that will be the closure of F, all possible FDs that we can infer from the given set of functional dependencies. Obviously, it will contain the set itself and the additional things, if possible, to infer. The Armstrong's axioms, the first three, mind it, I have 4, 5, 6 are the extension for easy inference, but the fundamental things are the Armstrong's axioms. We say these are sound and complete. Sound means say a functional dependency set is specified on relation R, then any functional dependency that is functional dependency set, say F, that is inferred from F using the Armstrong's axioms. That holds on R. That means any valid tuple satisfies the functional dependency. So basically, any functional dependency that will be inferring from the specified set, those are also valid on that particular relation. Those are correct. So that's why we said this is sound. Complete by successive application of Armstrong's axioms on F a complete set of FDs can be inferred. That is, we can get the closure of F by successive application of the Armstrong's axiom till there is no change. Till there is no change. Suppose say we are given X implies Y, say Y implies Z. Say this is Z. If we go on applying, so initially This is the closure. Closure is safe. Then we try to find whether by applying the inference rule we can make changes here or not. So see, readily we can say, okay, this is also can be inferred. So if we go on again on this, we try to apply the inference rule. If it is so that we cannot go further, then that is the closure or complete set. So as it is, whatever we infer using the Armstrong's axiom, those are correct, those are valid. So that's why it is sound, complete, because repeated application of the inference rules, it is possible to get the closure of the functional dependency set. So that way it is said this is complete. Suppose on a relation R, say the functional dependency set F, say these are given. Say X is an attribute or subset of attributes from R. X plus closure of set of attributes X. It means this is nothing but set of all attributes that can be determined by X. So looking into the functional dependencies, we can find out the closure of an attribute or set of attribute. That is also possible. So if we try to find this, say we want to find out the closure of X. So obviously initially X implies X. This is true. The trivial and the reflexivity rule I have one. Right? So X plus equals to X, that we can say this is our thing. Now we can say, okay, repeat. Apply inference rules. Say A implies B. Sorry. Apply each functional dependency. Say A implies B in F, or rather let me say for each. If we find that A is a subset of X plus, what does it mean? What does it mean? That it is possible to already in the X plus if we have A, that means by some way X determines A. A is it is already part of X plus. As A determines B, say X plus is having say A. So if there is a rule A implies B and A is a subset of X plus, then B can be inferred from X plus. If it is so, then X plus equals to X plus union B. B can be inferred, so that will be the part of this thing. Now how long shall we continue? Is it so that in one shot we will be looking into the functional dependencies? Finally, order of the functional dependencies, that will be important. Suppose we have X implies Y, say Y implies Z. So I have only two functional dependencies. I want to find out the closure of X. Then what I do? I'm taking this one. So x plus x initially is x, right? Now y is part of x plus, no. So I cannot consider z. Z cannot be defined. If I look into this x implies y. For this one, x is already part of x plus. So x plus will become x plus union y. So it becomes xy. Now see, if this one was tried next, then we could have included z here also. Because now y is part of x plus y, so z will be included in x plus. So this ordering, in which order the functional dependencies are being checked, that is important. So actually, we have to do this process recursively. How long? Say old x plus equals to x plus. So we have to repeat this until old x plus equals to x plus. Now see, if we now go this way, we are trying to find out the closure of x. So x plus equals to x plus equals to x. Getting inside, old x plus, it is having, what is the, at the beginning of this iteration, what is the value of x plus? That is being old here, so this is also x. Now, we are checking this one, so it will have no impact at this moment. Then looking for this one, so now y will be included. Now if we check, old x plus equals to x plus, no. So some changes has occurred. Maybe that the rules which were not applicable earlier, now may be applicable at this point of time. So again we repeat. So now the old x plus equals to x plus, that is it becomes xy. Again for each functional dependency A implies B. So look for this one. Now y is part of x plus. So z will be included. So x plus now equals to xyz. Check for this one. Already it is part of these things. What is the old x plus? This. So until old x plus x plus, they are not same. So some changes have occurred. So it will again try. Now next time old x plus is x plus means it becomes xyz. Now no additional change will come up. So x plus will remain xyz. Same it will come up. So these way we can find out. So at this point, this x plus, this will give us the closure of x. Now, if x plus equals to the schema, then x plus is a, then x is a candidate key. That is closure of an attribute. That is the schema. So that attribute determines all the attributes in the schema. So that is nothing but a candidate key. Right? So given the functional dependency set and the relation, if we have to find out the candidate key, what we can do? We can find out, say, schema it is having A1, A2, AN. So we can find the closure of A1 plus, A2 plus, A3 plus, A1 plus. If I want to find out the smallest candidate, there may be multiple candidates. So anyway, so we can find out whether any single attribute, closure of any single attribute is the schema. If it is so, those attributes itself will be the candidate. Otherwise, we can next, if there is no attribute with no single attribute, then obviously it will be a composite. Then we can find out which can be combined so that I can get the whole schema. So that way, using the given the functional dependency set and the relation, it is possible to determine the candidate keys. say given two functional dependency set, say E and F, say both specified on R. We say if covers E, they may not have the same functional dependencies. We say one set covers another one if each functional dependency in E is present in a class. So in that sense, suppose A and say E see, these two are not same, whether F covers E or not. So we have to find out the closure. So if we find out the closure, X implies Y implies Z. Apply the transitive rule, we can say X implies Z. So each functional dependency in E, it is present in the closure of these. So we can say F covers E. All the functional dependencies that may not be present here but can be inferred from it. But see, the reverse is not true. Reverse is not true. From here, we cannot infer anything else. Right? Apart from augmentation and all those kind of things, we cannot get any other new fundamental kind of thing. So see, it is present here. This one is not present neither in E. This is same as E plus also. It is not present in E plus. So here F covers E, but E doesn't cover F. Right? So anyway, so that is the meaning of cover. Two FD functional dependency sets are equivalent if two functional dependency sets, say E and F, are not specified on the same schema, are equivalent if F covers E and vice versa. In other words, if F plus equals to if their closure of the sets are same, then they are equivalent. Right? There is another curve, that is the minimal cover. So whenever we are talking about this minimal cover, so obviously the cover can have certain redundancy. So we want to get rid of that to obtain the minimal kind of thing. So here, first of all, we convert each functional dependency. X implies A1 into AN, or say replace each functional dependency of the form X implies A1 into AN with set of FDs. X implies A1, X basically applying the decomposition rule. Not IR4. Right? So that is the first step for easy implementation. So as if, see, X may be a set of attributes. So if we look like this, say X may consist of X1, X2, say Xn. So together they imply, say A1, they imply A2. So it's look like a cannon. So that's why this is also called canonical form. As if this is the muzzle, when you put the fire, this is election time, so everybody is firing. So, I mean, common people invariably will be the target. So already. So anyway, now see, say if covers E, a functional dependency set is covering this one. Now we want to find out the minimal cover. Then from that F which is covering E, the redundant part has to be removed. So this is the first step. Then next step, say the set is F. So we want to find out the minimal part that can be, we want to remove the redundancy. As if we want to find it F mean that will be covering F also. Obviously, if I get rid of the redundant things, it is the smallest cover for this one. Now see, for each functional dependency, say X implies Y. If see, one form of redundancy is that we are having some unwanted attributes here. See, this is of this particular form. On the right hand side, we are having only one attribute. Here we have a subset of attributes. Say, in your student relation, roll gives a score. So if I put additional things, that also valid. It itself can imply the score, can determine the score. If I put some additional things, then also it holds, but this is redundant. This is redundant. So we are trying to look for those. So from the set, if we remove this X implies A, so we will be getting a set with that that is B is a subset of X, of a subset of X. So from X, if we take away some part, and if it still holds, and so we have taken away this thing, we have removed this thing. Rather, I should not write it this way. Write it, better to write it in descriptive form. Say if B a subset of X and X minus B implies Y can be inferred from F minus X implies Y. Then F equals to, from F you remove X implies Y. With that said, take the unit. Right? So as if in X we have some additional attributes. So if it is so that if we remove X implies Y, and still we can consider, and if we consider that it can be still inferred, this it holds that if we take away apart from X, then the remaining part, if we take away apart from these and keep this the remaining part, if still this thing holds, can be inferred from rest of the, so this is no longer available from rest of the inference rules. If still we can infer this one, then why shall we keep this X implies Y? Remove this one, rather include this one. Right? So that is one way. So if we have some additional kind of things, additional attribute on the left hand side, remove those. Now, after this, we may have some rules which are redundant. Say, if I have X implies Y, Y implies Z, then X implies Z. This is redundant. This is redundant, right? That is the last step. For each functional dependency, X implies Y in F. If F minus X implies Y is equivalent to F, then F equals to F minus X implies Y. That means this is redundant. This rule itself is redundant. If we take away these things, the remaining part is equivalent to F. Then why shall we keep this one? Remove this one. So first of all, in the inference rules or in the functional dependencies on the left hand side. So here in functional dependency on left hand side, is there any redundant attribute? If so, remove. So that was the purpose here. Here, any redundant FD, if it is so, then remove this. Right? So that way we can find out, and this is the approach for finding the minimal cover. Now, with this idea of functional dependency, their equivalence, cover, minimal cover, closure of attribute, etc., etc. Now we will go for normalization. This is nothing but formal way of analyzing the schema as we mentioned earlier in the last class, subjected to key and functional dependencies. Now, obviously, these will come from the domain knowledge. In real life, we have to interact with your client, the users. They will specify what are the relationship among the data exists in that particular domain. We know the meaning of key. When you say key, basically it will refer to candidate key. Two other terms, prime attribute. Basically, this is an attribute which is part of prime attribute of a relation. Attributes or any attribute which is part of any candidate key is prime attribute. Suppose in our student relation, if we have roll number, registration number, etc., etc., we will show that this is also unique. So this is also a candidate key. This is also a candidate key. So then this is also prime attribute. This is also prime attribute. An attribute which is part of any candidate key, we will say those are the prime attributes. Then obviously rest are non-prime. Say in our result table, role, subject code, score. This is the candidate key. So this is also prime attribute. This is also prime attribute. And this is left as non-prime attribute. So we have multiple candidate keys. So all the attributes, those are part of those candidate keys. All of them are prime attributes. Rest are non-prime. Now, it is a process of, the formal process of refining a complex or fact schema into simpler ones so that the things that we discussed last day, so that redundancy is avoided, updation anomaly, that means insert, delete, modify. Updation anomaly is avoided. Occurrence of null value is restricted. So those are the goals, and we'll add on two more goals. One thing we discussed earlier, say on joining, as we'll be decomposing a fact relation into number of simple relations. On joining, no spurious tables are formed. Joining means equijoin based on common attribute. So this thing formally will say that if a schema is decomposed into number of simple schemas, that decomposition must be lossless. So lossless decomposition. Another is that dependency preserving. We have these functional dependencies. In our application, we must not violate these functional dependencies. So, a decomposition, it must ensure that the dependency is preserved. We'll explain this term later. But keep in mind, this is also, we'll talk on this too again later, in more elaborative form. So basically, this is the goal for normalization. Now, as earlier I mentioned that there are different levels of normalization. Say first normal form, second normal form, third normal form, fourth, fifth. It's like that. I've stopped right now at this point because commercially we will be dealing with these ones. Still, I'll talk about the fourth normal form, and there is another BCA. So we have to follow this way. So a relation is in say K normal form. It means it satisfies first normal form, second normal form, up to K normal form. So all the lower levels are also satisfied. Now, all the time, we may not go for the highest level of normalization. Always highest level of normalization may not be done. So if it is so, making a compromise, so certain redundancies may be allowed by not going for higher form. It was possible to go for higher form. It is applicable. Still, we may not go for, not going for higher form. That it was possible that after we have to move up to 280. We can find that situation for third NF is there. So if we don't go for that, some redundancy will be there. Still, we may say that stick to the lower level. If it is so, this is known as denormalization. In the course of describing the normalization, that time I may refer. That's why we may like to go for the lower level. Or what that happens? Suppose you have employee and the department or student and the department, everything together. It has some problem. But sometimes people may like for that also. So very often, every now and then, I mean this example, practically this will not be very good. Say, for the students, if I have, say, roll name, marks in 5 subjects and total marks. There is a dependency. Total marks can be obtained from, as we have talked about the derived attributes also. That if we allow some redundancy and in our frequent requirement, if it is so that in order to support that, if I want to get rid of the redundancy, then frequently we have to go for lots of other computations and other operations. That is a frequent requirement. Now, in that case, if the rate of service becomes important, that I should be able to respond in a very rapid manner, then I may like to avoid those computation or gathering information from so many places. Rather, despite of the problems of redundancy, I may like to put everything together. So some redundancy we may allow for that. So if it is so that it was possible to go for the higher level of normalization, but we are not going for that. We are keeping ourselves at the lower level. It is known as denormalization. So denormalization, for practical purposes, sometimes it may be required. So, okay, let us stop today. So in the next class, we will start from this first normal, second normal, and third normal form, and subsequently this area, fourth normal form, like that. Okay. So again, so let us stop today.